Hi, welcome to my YouTube channel. Today I'll be building a car collision warning system using an Arduino. Today's video will be broken up into two parts. Part 1 will go over how to use an ultrasonic sensor and the Arduino. Part 2 will go over how to make the power supply for the Arduino. Now, before we can start the assembly of our circuit, we'll first have to understand how our ultrasonic sensor actually functions. Now, an ultrasonic sensor is a device that essentially measures the distance between itself and whatever object is in front of it by using ultrasonic waves. And for the time being, we'll label this distance as D, and it is what we will be trying to solve for in the rest of this little tutorial session. Now, we can start off this investigation by looking at the pinouts of our sensor right here. And we see that the sensor actually has 4 pinouts: ground, echo, trigger, and VCC. Right off the bat, we can tell, or we can infer, that the ground pin will be connected to the ground of the Arduino, and the VCC will be connected to the 5-volt power supply that we have. But we'll have to do a bit more. I will have to do a bit more explaining to talk about how the trigger and echo pins work. But before we can get into that, we'll first have to take a closer look at the physical sensor we have here. Now, when you look at it, you'll see that there are these 2 little cylindrical modules that are attached to it. And on the side of the sensor, we actually have the letters T and R. And what these letters stand for is that one of these little modules is an ultrasonic transmitter, and the other one is a ultrasonic receiver. And what that means is that at one point, one of these modules will send out an ultrasonic wave, and the other one is designed to read one. And that's where our trigger pin comes in. When we send in a quick 5-volt pulse to our trigger pin, our ultrasonic transmitter will send out a quick ultrasonic pulse, or wave, whatever the fancy technical term for that is. And once that wave is sent out, it will then collide with whatever object is in front of it and reflect. And as that wave makes its way back towards the sensor, it will then collide with the receiver of our SO4 ultrasonic sensor. And once it collides with that receiver, we will get a quick 5-volt output pulse. Now we know that we send in a signal to a trigger pin, we send out an ultrasonic wave, and when that wave comes back towards us and hits our sensor, we'll then get a quick 5-volt pulse again. So now you might be wondering, okay, we get 2 5-volt pulses, how is that going to help us find the distance between our object and whatever is in front of it? And that we'll have to use a bit of physics. Now, one of the first things you learn in physics is that velocity, which is the speed of an object, is equal to the distance that object moves over the amount of time it takes that object to move said distance. And as we see here, D is the x variable or displacement that we are trying to find. And we can easily find T by measuring the amount of time it takes for us to get an echo signal back after we sent our initial trigger signal. So then we can move those 2 variables here to find T. And then if we do a bit more thinking, we'll find that the amount of time it takes for us to get our echo signal after we send out our trigger, the wave must have moved twice our distance, twice the distance between the sensor and whatever object is in front of that. And with this logic, we can easily come up with the equation right here, which is V, or the velocity of the ultrasonic sensor, equals the distance that between the sensor and whatever object is in front of it, divided by the time it takes for us to get an echo signal, divided by 2. And since the velocity of an ultrasonic sensor is a universal constant, at least on planet Earth, and we can easily find T by using a timer on our Arduino or something similar, and the only variable we need to find is D, we can do a simple algebra to find that V of the ultrasonic sensor times T, or time divided by 2, equals D. Now Now we can finally start assembling our circuit first. We'll need to bring in our ultrasonic sensor and we'll hook that up to the 5-volt power supply in the ground on our Arduino. After that, we will connect digital pin 12 on the Arduino to our trigger pin, and then we will connect digital pin 11 to the echo pin on our ultrasonic. We will then take our buzzer and connect the 5-volt input on our buzzer to digital pin 9 on the Arduino, and then we will connect two resistors in series with each other. I chose two 220 ohm resistors, or you could use a single 440 ohm resistor, and we will connect that to the ground of the buzzer, and then we'll connect that to the ground of our buzzer, and that should be all you need to do for this after project. Alright, this first section of code that you see right here is where I declare the pin values for all of the pins that we're going to use. We have one for the buzzer, trigger, and echo pin. I've also declared the safety distance, aka the distance that an object should get close enough to the sensor where the sensor would set off its buzzer as 5 inches. And the duration variable is where I'm going to store the amount of time between the initial trigger pulse and the echo pulse that we get from the sensor. And the centimeter and inches variable is where I'm going to store the distance reading that we calculate using the duration variable. In the voice setup, which is essentially the part of the code that will be run only once, I start off with our serial begin, where I set off the baud rate at 9600. This is only going to be used for the serial plotter that you can see to read out our centimeter and inches variables at real time. I then declared the buzzer and trigger pin as outputs, and I've declared the echo pin as a digital input. And then we go to the void loop of our statement. This is the code that will be run continually, like after the voice setup, and it will be pretty much run as long as the Arduino has power. In this first section right here, this is where we send out our initial trigger pulse, and we tell the ultrasonic sensor's transmitter to send out its first, ultrasonic pulse to whatever is in front of it. We then, and then in this statement is when we tell the Arduino to time the amount of time between when we send out our first trigger pulse and when we receive our first pulse from the echo pin. And then we take this duration, or the pulse, the time that we measure, divide that by 2 and multiply it by 0.034, which is the velocity of the ultrasonic wave. And then we have another equation here that converts the centimeters to inches, because I am doing this from the US. And in this statement right here, we just print out the distance measurements that we received. You don't really need this when you're in real life, but it's nice to have so you're able to double check and make sure all of the measurements are correct. And in this final if-else statement that you see in the bottom right here, we state that if the measured distance that we have just read is less than the distance less than our safety distance or equal to it, we will set off our buzzer, where we will turn on our buzzer and send out a sound wave at like 500 hertz, I believe. And if that contention is not met, we will not turn on our buzzer. And that's pretty much all I need to know for the code. Now we will go over part 2 of this project. The TP4056 is a battery charging module. The TE110 is a 3.7 volt to 5 volt boost converter. And the 18650 is the battery used to power this project. Now it's time for the final part of our project, which is a power supply assembly. We'll start this off by connecting the positive and negative terminals of our 18650 battery to the positive and negative input terminals of our TP4056. And once we have finished with that, we will then connect the output terminals from the TP4056 to our TE110. And it's important to remember when you're doing this, it's best to add a switch into either the positive or negative wires from TE110 to TP456. because you cannot charge your battery while you are drawing current from it. And if you were to do that, you could possibly damage the circuit. Okay guys, so this is what the final part of the project should look like. On the left here you see that we have our pseudo battery pack. I glued the TP456 and TE150 onto a piece of balsa wood, and I just hot glued that to our battery. And I just flick the switch, and our Arduino should be turned on, and I can just put my hand over it, and a small buzzer goes off. One note in the future, if I do this project again, is that I will try and use lower value resistors so that the buzzer is a lot louder, and I'll see if I can find a way to use up less of the board, because I have like this whole section that's kind of wasted. So my soldering skills aren't the best, and we'll try and improve upon it. This is what the back of the PCB looks like. And one thing that really surprised me is the performance of this battery pack. I only spent like a couple dollars on it, and I actually salvaged this battery from a broken laptop I have at home. As you can see, it was quite damaged, but it still managed to work out. I get about maybe 5 to 6 hours of battery life in it, and that's in like the worst case scenario. The battery's not fully charged. I can easily see this working for like I can easily see the circuit being powered for like an entire day on this battery. And yeah, I'll probably be using this, or the battery schematics I use, for other projects in the future. If you liked today's video, please subscribe to my YouTube channel and leave a comment down below on how I can improve this channel. This is my first YouTube video. Other than that, have a great day.